Tonight, we follow the story of Voyager, the small spacecraft that has traveled farther from Earth than any machine in human history. Welcome to the Orbit for Sleep channel. Let us follow the orbit of science and drift gently towards sleep. Voyager is now so far from Earth that its distance can only be understood through careful measurement. The spacecraft has been traveling outward since 1977, moving through the solar system with no engine pushing it forward. Instead, it continues on its path because of its initial launch speed and the deep emptiness of space. There is nothing significant to slow it down, so its motion remains steady, like a small seed carried by a gentle but endless breeze. Today, Voyager is more than 24 billion kilometers away. This number is large enough that it becomes difficult to picture, so scientists track the distance using radio waves. Radio waves are a form of light that travels at the fastest speed possible in the universe. NASA sends a signal from Earth. The signal reaches Voyager, and then Voyager sends a response back. The time it takes for the signal to make the round trip tells us how far away the spacecraft is. Even at light speed, the message can now take over 18 hours just to reach Voyager. The measurement process is simple in idea, but demanding in practice. The radio signal becomes weaker as it spreads out through space, much like a whisper fading across a wide desert. By the time the beam reaches the spacecraft, it is faint enough that only large and sensitive antennas can detect it. The dishes of the Deep Space Network, which are placed in California, Spain, and Australia, listen constantly for Voyager's reply. Their size and placement allow Earth to maintain contact even as the planet rotates. Voyager's increasing distance creates a sense of quiet isolation. Its movement is smooth, with no sudden acceleration or obstacles. The darkness around it is not a complete void, but a thin sea of particles, dust, and faint magnetic fields. Against this backdrop, Voyager continues outward at more than 15 kilometers per second, fast enough to circle Earth in less than half an hour. Yet compared to the distances between stars, its speed is gentle. To understand the scale, imagine Earth reduced to a single grain of sand. Voyager would now be several meters away from that grain, continuing on a straight path. But the nearest star would still be thousands of kilometers farther. The spacecraft's incredible distance from Earth is impressive, but in the larger structure of the galaxy, it remains in the neighborhood of its birthplace. Scientists monitor the signals every day, updating the distance and observing how the surrounding environment changes. Each measurement is a reminder of how far human technology has reached. The numbers on the screen are not just data, they are the record of a small craft that has traveled farther than any other object built by human hands. Voyager's distance also reveals something subtle about the nature of time. Because we see only the light that has had time to reach us, we are always observing the spacecraft as it was many hours ago. The spacecraft moves steadily forward, and the information about its position drifts behind it, like a slow echo in space. This delay becomes a part of its identity, shaping the way we experience its journey. The measurement of Voyager's distance is therefore not only a technical achievement, but also a reflection of the vastness of the universe. The numbers grow slowly, steadily, and predictably. They remind us that even something as small as a spacecraft can travel enormous distances when given enough time. And they show how patient observation allows us to follow its path, even across the silent depth of interstellar space. Voyager crossed the boundary of the heliosphere, known as the heliopause, after decades of steady travel. The heliosphere is a large bubble created by the sunday. It forms because the sun constantly releases a stream of charged particles called the solar wind. These particles spread out in all directions, creating a protective cocoon around the solar system. Inside this bubble, the sun's influence is strong. Outside it, the space between stars begins. The heliopause marks the point where the solar wind becomes too weak to push against the material of interstellar space. Interstellar space is filled with thin gas, dust, and magnetic fields, but it is much denser than the outermost edge of the heliosphere. The boundary between these two regions is not solid. Instead, it is more like the gradual edge of a very thin fog meeting another, slightly denser fog. Voyager detected this transition by measuring changes in particle density and magnetic direction. When Voyager crossed the heliopause in 2012, scientists confirmed it by observing a sharp rise in the number of high-energy particles called cosmic rays. Cosmic rays originate from distant stars, supernovae, and the general activity of the galaxy. Inside the heliosphere, many of these particles are blocked or slowed by the sun's magnetic field. Outside the heliosphere, they flow more freely. The moment Voyager recorded this increase, researchers knew it had finally entered interstellar space. The transition was not dramatic in appearance. From Voyager's point of view, the darkness looked the same as before. There was no visible line, no obvious change in scenery, but the environment around the spacecraft shifted in measurable and steady ways. The gentle pressure from the solar wind dropped. The particle density increased slightly. The magnetic field orientation changed direction. These subtle clues formed a quiet but clear signature of crossing a boundary that no spacecraft had ever passed before. The heliopause itself is not fixed. It expands and contracts over time, depending on the strength of the solar wind. When the sun is more active, the bubble grows. When it is quieter, the bubble shrinks. Voyager happened to reach the boundary during a period when the heliosphere was relatively compressed. This timing allowed it to cross sooner than earlier predictions suggested. From Earth, the event carried deep meaning. It was the moment when a human-made object first left the space dominated by our star and stepped into the vast region between the stars. Even though Voyager still moves within the sun's gravitational influence, it now travels through a region shaped by forces beyond the solar system. To imagine this crossing, picture a small boat drifting across a calm sea. For many years it floats within the gentle push of a steady breeze. Then, slowly, the breeze fades, and the boat drifts into air shaped by distant winds. Nothing obvious changes in the sky or water, but the forces guiding the motion shift. Voyager experienced something similar. Its path remained steady, but the environment controlling that path changed from solar to interstellar. Voyager's entry into interstellar space marked a milestone in the history of exploration. It demonstrated how far technology built in the 1,970 seconds could travel, and how patient measurement can reveal invisible structures. The heliopause is one of the largest boundaries humans have ever mapped, and Voyager traced its shape by simply drifting outward. This crossing also reminded scientists of the delicate structure of the solar system. The sun's influence does not end abruptly, but fades slowly with distance. Voyager captured this fading in detail. It recorded the thinning of the solar wind, the shift in magnetic fields, and the soft transition into the deeper sea of the galaxy. Each bit of data shows how the sun's reach interacts with the wider universe. Voyager now continues forward through interstellar space, carrying the memory of its crossing with it. The boundary it passed is far behind, but the information it gathered helps us understand where the solar system ends and the galaxy begins. Voyager has been traveling outward since 1977, covering an immense distance over nearly 5 decades. Its speed and travel time are key to understanding how it reached interstellar space without any further propulsion. During its launch, Voyager received a powerful push from the rocket that carried it, sending it beyond Earth's gravity. Later, it gained additional speed through gravity-assist maneuvers, close flybys of Jupiter and Saturn, that redirected and accelerated the spacecraft using the planet's gravity. These flybys acted like slingshots, giving Voyager enough momentum to leave the outer solar system. Since then, Voyager has no engine running. It moves forward simply because nothing in space slows it down. Space is not completely empty, but it is empty enough that the tiny particles it encounters cannot significantly affect its motion. Voyager travels at more than 15 kilometers per second, a speed fast enough to move from one side of Earth to the other in a few minutes. Yet in the scale of the cosmos, this speed remains gentle and gradual. The long travel time helps illustrate the enormous scale of the solar system. Even at its high speed, Voyager took more than 12 years to reach Neptune's distance from the Sun. It required over 3 decades to come close to the heliopause, the boundary where the Sun's influence fades. Every additional year of its journey adds billions of kilometers to its distance from Earth. But the outer regions remain vast compared to anything within the inner solar system. Voyager's steady movement gives scientists a clear timeline of its location. Since its launch, the spacecraft has traveled continuously, with no major events interrupting its outward drift. The predictability of its path is part of what allows NASA to keep track of it with such precision. Engineers calculate its position based on the time signals take to reach it, combining this data with knowledge of its speed and direction. Thinking about Voyager's travel time also brings attention to the endurance of its instruments. Most devices on board were designed to operate for a few years, not several decades. Over time, many have failed or been turned off to conserve power. The ones that remain active still send valuable information back to Earth, though their strength has weakened. The spacecraft carries a radioisotope generator that slowly loses power each year, limiting what can remain operational. The long journey through space also changes the way Voyager experiences its environment. In the early years, the spacecraft passed through regions filled with solar wind, magnetic interactions, and the gravitational pull of the giant planets. As it moved farther away, these influences became weaker. The spacecraft now drifts through a region where the sun's presence is faint, and the environment is shaped more by the galaxy itself. Its decades of travel illustrate how far something can move when no resistance acts upon it. On Earth, objects slow down quickly due to friction, air resistance, and gravity. In space, Voyager continues forward with no need for additional force. Its long journey highlights the fundamental principle of motion. An object in motion stays in motion. unless acted upon by another force. To imagine the journey, picture a single spark drifting away from a fire. At first, the spark feels the heat and turbulence nearby. As it floats farther, the environment becomes calmer and quieter. Eventually, the spark drifts into still, dark air, continuing in a straight line. Voyager's path resembles this image. It began in a busy region full of planets and solar activity, then moved into a quieter area where the sun's influence fades. Nearly half a century has passed since its launch, yet Voyager remains one of the fastest and most distant human-made objects. Its travel time is not only a measure of distance, but also a reminder of the patience required in space exploration. Understanding its speed and the decades it has been moving helps us appreciate the vast scales involved in the solar system and beyond. Voyager's journey continues, still propelled by the momentum it gained long ago. As time moves forward, the spacecraft drifts deeper into the galaxy, carrying with it the memory of the early solar system and the story of how far human curiosity can travel. Tracking a spacecraft as distant as Voyager is simple in idea but extremely delicate in practice. The basic method is straightforward. Earth sends a radio signal, Voyager sends one back, and the round-trip time reveals its distance. But performing this task across more than 24 billion kilometers turns a simple concept into a precise scientific challenge. Radio waves travel at the speed of light. Even so, a signal now needs over 18 hours to reach Voyager and another 18 hours to return. Every command and every response carries this built-in delay. Engineers speak to Voyager as it existed many hours ago, and the spacecraft answers with information from its own distant past. To detect signals this faint, NASA uses the Deep Space Network massive radio antennas in California, Spain, and Australia. These dishes can detect signals weaker than a whisper spread across a continent. By the time Voyager's signal reaches Earth, its strength has faded to almost nothing, yet the antennas still capture it because they are designed with extreme precision. The antennas also measure tiny shifts in the signal's frequency caused by the Doppler effect. These shifts reveal Voyager's speed and direction, even though no camera can see it. The data forms a steady map of the spacecraft's motion, updated with every faint reply. Voyager's own transmitter is weak and old, built in the 1970 seconds. It must keep its small antenna pointed at Earth with great accuracy. Small thruster pulses correct its orientation, ensuring the narrow radio beam does not drift away. As long as the antenna remains aligned, the connection holds. Communicating with Voyager requires patience. A single exchange takes nearly a full day, so instructions must be simple and carefully planned. This slow rhythm matches the quiet pace of the spacecraft's journey through the outer darkness. Tracking Voyager is not only a technical task, but also a measure of our persistence. With faint signals and long delays, scientists continue to follow a tiny machine drifting at the edge of the sun's influence. Each successful whisper from Voyager shows how far careful engineering and human curiosity can reach. When we say Voyager has reached interstellar distance, the phrase sounds final, as if the spacecraft has crossed into a completely new world. In reality, the scale of space makes even billions of kilometers feel small. Voyager is far from Earth, so far that light itself needs many hours to travel between us. But this distance is still tiny compared to the separation between stars. Inside the solar system, distances grow quickly. Earth is about 150 million kilometers from the Sunday. Neptune is 30 times farther. Voyager now travels far beyond that, more than 24 billion kilometers away. These numbers feel enormous, yet they are still only a fraction of the distance to the nearest star. The closest star system, Proxima Centauri, is more than 40 trillion kilometers away. Even traveling at more than 15 kilometers per second, Voyager would need tens of thousands of years to reach a similar distance. This contrast reveals the true meaning of interstellar scales. The solar system, large as it seems, occupies only a small bubble in the galaxy. The space between stars is vast, filled mostly with thin gas, dust, and magnetic fields. Voyager has entered this region, but it remains close to the Sun on the scale of cosmic geography. If the Milky Way were a wide ocean, Voyager would have just stepped a few meters beyond the shoreline. To picture this difference, imagine shrinking the Sun to the size of a lamp. Earth would be a grain of sand circling close by, and Voyager would be a tiny speck drifting far away from the lamp. But the nearest lamp, the next star, would be several kilometers in the distance. Voyager's distance is impressive from a human perspective, yet still a first step into a much larger landscape. This understanding also shapes how scientists describe Voyager's journey. When they say it has entered interstellar space, they mean it has crossed the boundary where the Sun's solar wind loses its influence. They do not mean it is close to another star or approaching a new system. Instead, the spacecraft now moves through an immense region dominated by forces from the galaxy as a whole. Interstellar distance becomes meaningful not because Voyager is near something new, but because it is no longer confined to the environment shaped by our Sunday. It now travels through a medium shared by countless stars, supernova remnants, and ancient magnetic fields. The change is subtle yet profound, less a destination, more a shift in context. The phrase also reminds us of the limits of our own intuition. Human senses are built for Earth's scale. We understand meters, kilometers, and perhaps the distance across a city. But the distances between stars stretch our imagination. Voyager helps bridge this gap, turning abstract numbers into a real, ongoing journey. Understanding what interstellar distance truly means adds depth to Voyager's mission. The spacecraft has not arrived somewhere. It has simply begun moving into the vast, quiet space between the stars. Its path will continue for thousands, even millions of years, long after Earth and the Sun have changed. Each kilometer it travels is a reminder that space is far larger than our instincts suggest, and that Voyager's journey has only just begun. Voyager now travels through the interstellar medium, the thin material that fills the space between stars. Although the word medium may sound dense or substantial, this region is almost completely empty. On average, each cubic centimeter contains only a few atoms, far fewer than even the best vacuum created on Earth. Yet this sparse environment holds important clues about the galaxy, and Voyager is the only spacecraft close enough to measure it directly. The interstellar medium is made of plasma, dust, and magnetic fields. Plasma is a state of matter similar to gas, but with charged particles, electrons, and ions that can move freely. These particles respond to magnetic fields, creating subtle currents and flows. Voyager's instruments detect these tiny changes, allowing scientists to understand how the energy of the galaxy spreads through space. In addition to plasma, there are small grains of dust drifting between the stars. These particles are leftovers from ancient stars that exploded long ago. Over millions of years, the dust spreads out, forming a thin haze across the galaxy. As Voyager moves through this region, it encounters these particles one by one. They are so small and so far apart that the spacecraft feels no resistance, yet the data it collects helps reveal the long history of stellar evolution. Magnetic fields are another essential part of the interstellar medium. They stretch across space like invisible threads, shaped by the movement of stars, supernova explosions, and the rotation of the galaxy. Voyager measures the direction and strength of these fields, offering insight into the structure of the Milky Way's magnetic environment. Even though the magnetic fields are extremely weak, they influence the behavior of charged particles over great distances. The environment Voyager is entering is much different from the solar wind region it left behind. Inside the heliosphere, the sun's influence is strong. Charged particles rush outward, creating pressure and turbulence. In the interstellar medium, the overall density is higher, but the pressure is more uniform, and the magnetic fields follow patterns shaped by the galaxy rather than by a single star. Voyager's sensors detect this shift through changes in particle density, temperature, and field direction. From Voyager's perspective, the change is not visible. The darkness around the spacecraft looks the same, but the data shows a clear transition. Particle counts rise slightly, the plasma becomes cooler, and the magnetic field orientation rotates. These details help scientists build a three-dimensional picture of the galaxy's outer environment, something no other spacecraft has achieved. To imagine this region, picture a quiet ocean that stretches endlessly in all directions. The water is so thin that each droplet is separated by meters of empty space, yet the ocean still carries slow-moving currents and faint ripples shaped by distant storms. Voyager drifts through a similar environment, calm, sparse, but full of the galaxy's history. Studying the interstellar medium helps scientists understand how stars form and how stellar material spreads across the galaxy. The region Voyager now explores is made of matter once inside long-dead stars. Some of this material will eventually gather, collapse, and ignite into new suns. Voyager is not only traveling through space, it is moving through the remains of ancient cosmic cycles. By measuring the interstellar medium directly, Voyager provides rare information about a region that humans have only studied from afar. Its data helps confirm theories about how the galaxy behaves and how energy moves through the vast space between stars. Even though the interstellar medium appears empty, it holds the clues to the life cycle of galaxies. Voyager's journey through this subtle environment marks the beginning of a new chapter in exploration. Each reading it sends home adds to our understanding of the galaxy and our place within it. The spacecraft continues forward, carrying instruments built decades ago, still sensitive enough to touch the faint structure of the universe beyond the sun's reach. Cosmic rays are some of the highest energy particles in the universe, and Voyager is now in a region where they flow freely. These particles come from powerful events such as exploding stars, fast-moving shock waves, and the energetic environments around black holes. When cosmic rays arrive at Voyager, they strike its detectors one by one, each impact offering a glimpse into processes happening far beyond the solar system. Cosmic rays are mostly protons, which are tiny particles found inside atoms. They travel close to the speed of light, carrying enormous energy despite their small size. Inside the heliosphere, the sun's magnetic field blocks many of them, acting like a protective shield. But once Voyager crossed the heliopause, this shield weakened, and the number of cosmic rays around the spacecraft increased sharply. This rise was one of the clearest signs that Voyager had entered interstellar space. Voyager's instruments that measure cosmic rays are old but still sensitive. The spacecraft carries detectors designed in the 1,970 seconds that count particles and measure their energy. These detectors do not take images or record shapes. Instead, they simply register each time a high-energy particle passes through. From these simple measurements, scientists can determine how many cosmic rays are present and how energetic they are. The pattern of cosmic rays tells researchers about the environment surrounding Voyager. In interstellar space, the flow of particles is steadier and stronger. The energies are higher because the particles have traveled across vast distances without being slowed by the sun's influence. By studying these energies, scientists learn about the forces that accelerate particles across the galaxy. Cosmic rays also trace the structure of magnetic fields. As the particles move, magnetic fields bend their paths slightly. By observing how the number of detected particles changes over time, scientists can map the direction and strength of the magnetic fields around Voyager. Even though these fields are extremely weak, they guide cosmic rays like faint currents in a quiet ocean. The spacecraft itself feels nothing from these particles. Cosmic rays do not push or slow it, but they do leave tiny marks, signals that tell a story about the galaxy's activity. Each detection is a reminder that Voyager is moving through a region shaped by ancient explosions and energetic events scattered across the Milky Way. To imagine cosmic rays, picture fine grains of dust blown by distant storms, moving through a calm night sky. You cannot see the grains, and you cannot feel them, but they whisper information about storms that happen far away. Voyager listens to these whispers. The data it sends back helps scientists understand how energy moves through the galaxy and how violent events in distant regions affect the space between stars. Cosmic rays are invisible to human senses, but to Voyager, they form a steady background pattern. Their presence reveals the true nature of interstellar space. Calm in appearance, yet filled with particles carrying the memory of powerful cosmic events. By measuring them, Voyager continues to extend our reach into the deeper structure of the Milky Way. Even at Voyager's extreme distance, the sun continues to shape the space around it. The spacecraft has moved beyond the heliopause, where the solar wind no longer dominates, but the sun's magnetic field and gravity still reach far into interstellar space. Understanding this influence helps explain why Voyager's journey is both independent from the solar system and still quietly connected to it. The sun emits a constant stream of charged particles known as the solar wind. Close to the sun, this wind is strong, pushing outward in all directions. Farther away, it becomes weaker as it spreads across a growing sphere of space. Eventually, it reaches a point where it can no longer push against the surrounding interstellar medium. This point is the heliopause, the boundary Voyager crossed. Beyond it, the solar wind fades, but traces of the sun's magnetic influence continue. The sun's magnetic field extends far beyond the heliosphere, carried outward by the solar wind like threads stretching into space. Even after the solar wind loses its strength, the magnetic field lines remain, though they become distorted and mixed with the magnetic fields of the galaxy. Voyager's instruments detect these faint, twisted lines. They reveal how the sun's influence blends gradually into the wider magnetic environment of the Milky Way. Gravity reaches even farther. Unlike the solar wind, gravity does not weaken in sudden steps. It decreases gently with distance, but it never disappears. Voyager remains under the sun's gravitational pull and will continue to orbit the galaxy as part of the solar system's extended family. Even billions of kilometers away, the spacecraft's path is still shaped, in part, by the sun's presence. Although the sun's effects are now subtle, they left strong marks on Voyager's earlier journey. In the inner solar system, the solar wind was fast, hot, and energetic. Magnetic storms and solar activity created ripples and shocks that Voyager recorded as it passed Jupiter, Saturn, Uranus, and Neptune. As Voyager traveled outward, these influences grew quieter, but they never vanished completely. In interstellar space, the environment becomes smoother. The pressure is steadier, and the magnetic fields follow large-scale galactic patterns rather than the swirling structure of the solar wind. Voyager senses this difference through changes in particle density and magnetic direction. The shift reveals the slow fading of the sun's influence, a kind of long twilight where one environment ends and another begins. To imagine this transition, think of walking away from a warm fire on a cold night. Close to the flames, the heat is strong. As you step back, the warmth weakens but does not disappear immediately. Eventually, the heat fades into the cool air around you, yet you can still sense where the warmth used to be. Voyager's journey reflects this same gradual change. The persistence of the sun's influence shows how connected the solar system remains, even at vast distances. Voyager has entered interstellar space, but the traces of its origin continue to follow it. The spacecraft moves through a region shaped by the galaxy, yet the sun leaves a faint imprint on everything it encounters. By measuring these final signs of solar influence, Voyager helps scientists understand the true size and shape of the heliosphere. It shows where the sun's environment transitions into the galaxy's wider domain. Each reading adds clarity to this complex boundary and deepens our understanding of how our star interacts with the universe beyond it. Communication with Voyager reveals one of the most fundamental limits of the universe. Nothing can travel faster than the speed of light. Even though radio signals move at this maximum speed, the vast distance between Earth and the spacecraft creates a long delay. This delay shapes every exchange of information and becomes an essential part of understanding how Voyager operates so far from home. A radio signal traveling at light speed covers about 300,000 kilometers each second. That seems incredibly fast. Yet the space Voyager has crossed is so large that the signal now needs more than 18 hours just to reach it. After Voyager receives the message, it sends a reply that takes another 18 hours to return. This means the round-trip communication time is nearly a full day. Engineers must wait patiently for every confirmation, every piece of data, and every adjustment. This delay affects how Voyager is controlled. Commands cannot be sent quickly or corrected immediately. Instead, each instruction must be simple, reliable, and planned far in advance. If an unexpected event occurs on the spacecraft, engineers cannot respond instantly. They must observe the data, interpret what happened, prepare a response, and then wait again for confirmation. The delay also limits what Voyage can attempt. It cannot rely on rapid communication with Earth to navigate or operate its instruments. Instead, its systems were designed to function independently. The spacecraft follows preset routines and uses automatic protections to keep itself safe. These features were built into Voyager decades ago, long before it reached its current distance. The light speed delay also tells scientists something important about distance itself. Because we can communicate with Voyager only at the speed of light, we always see it as it existed many hours ago. The information that arrives is not about Voyager in the present moment. It is about Voyager in the past. This effect becomes stronger the farther the spacecraft travels. Over time, the gap between its actions and our knowledge of them continues to widen. This idea reflects a fundamental truth about the universe. Information takes time to travel. Even light cannot cross space instantly. When we observe distant stars and galaxies, we see them as they were thousands or millions of years ago. Voyager gives us a smaller, more personal example of this principle. Each message it sends carries a timestamp created by the speed of light. To imagine this, picture shouting across a large canyon. You hear the echo a moment later, delayed by the distance it travels. Voyager's communication works in a similar way, but on an unimaginable scale. The spacecraft sends back a whisper so faint that only the largest antennas can hear it, and the echo takes most of a day to arrive. The delay also creates a unique emotional distance. Voyager continues forward millions of kilometers farther each day, and we follow its journey through signals that arrive long after they were sent. Yet despite this separation, the connection remains steady. The faint radio waves remind us that even across the emptiest regions of space, communication is still possible. Understanding the light speed limit helps explain the nature of Voyager's mission. The spacecraft cannot operate as if it were close to Earth. It must move slowly, carefully, and independently, with each exchange shaped by the long journey its signals must travel. This limitation is not a flaw, it is part of the beauty of deep space exploration. The delay becomes a quiet rhythm, marking the passage of time and distance. It reflects the vastness of space and the patience required to explore it. And through this slow, steady exchange, Voyager continues to share its story from a place no other human-made object has ever reached. Voyager survives in deep space because of a small but powerful energy source called an RTG, or radioisotope thermoelectric generator. This device uses heat from the natural decay of a radioactive material, plutonium-238, to create electricity. There is no engine, no solar panel, and no sunlight strong enough at Voyager's distance. Instead, the spacecraft relies entirely on this steady, fading heat. Inside the RTG, pellets of plutonium-238 release heat as they undergo radioactive decay. This heat flows through metal plates that convert temperature differences into electrical power. The process has no moving parts, which makes the system extremely reliable. When Voyager launched in 1977, the RTG produced enough electricity to power all instruments, heaters, and communication systems. But the power drops a little each year. Plutonium-238 has a half-life of about 87 years, meaning it slowly cools over time. As the heat decreases, the RTG generates less electricity. Engineers must decide which instruments to keep running and which to turn off. Over the decades, many devices have been shut down to conserve power, leaving only the essential instruments still active. Despite this decline, the RTG has performed far beyond its expected lifetime. It was originally designed to last only about a decade. Instead, it continues to operate nearly 50 years later. The steady output of the RTG keeps Voyager warm enough to function in the extreme cold of interstellar space, where temperatures approach absolute zero. Without this heat, the spacecraft's electronics would freeze and fail. The power limitations shape every part of Voyager's mission. Engineers carefully schedule when instruments turn on, how much data they send, and how long each measurement lasts. They also reduce the strength of the radio transmitter to conserve energy, even though this makes Voyager's signal even fainter. Every watt matters. The spacecraft now operates on less power than a household light bulb. To imagine the RTG's role, picture a single glowing ember keeping a traveler warm in a vast frozen wilderness. The ember is small, but it burns steadily and predictably. Voyager's RTG is that ember, quiet, persistent, and essential. It allows the spacecraft to continue its journey long after solar power became impossible. The slow decline of the RTG also reflects the passage of time. Each drop in power marks another year of travel. The fading electricity serves as a reminder that Voyager was built during an earlier era of exploration, using technology that has outlived the team who designed it. Still, the RTG continues to provide enough energy for core operations. As long as it produces even a small amount of heat and electricity, Voyager can keep listening, measuring, and sending whispers back to Earth. This power source is the heart of the spacecraft, simple, reliable, and enduring, carrying Voyager through the silent dark between the stars. Voyager carries one of the most symbolic artifacts ever sent into space, the Golden Record. This record is a message from Earth, created to represent humanity, our sounds, our languages, and our place in the universe. Its purpose is not practical navigation or scientific measurement. Instead, it serves as a cultural time capsule, meant for any distant intelligence that might one day encounter the spacecraft. The Golden Record contains greetings in 55 languages, recordings of natural sounds like wind, rain, waves, and birds, and music from many cultures and eras. It also includes images encoded as analog signals, pictures of landscapes, animals, scientific diagrams, and scenes from daily life. The content was chosen to show both the diversity and the unity of life on Earth. Even if the viewer does not understand our languages, the record offers patterns and visuals that reflect curiosity, learning, and communication. The message begins with instructions. Etched onto the cover are diagrams, explaining how to play the record, how to interpret the encoded images, and where our solar system is located relative to a set of pulsars. Pulsars are rapidly spinning stars that emit regular bursts of radiation. Because each pulsar has a unique timing pattern, they can serve as cosmic landmarks. By identifying these patterns, a distant civilization could determine when and where the record originated. The creation of the Golden Record was led by a small group of scientists, artists, and thinkers. They selected sounds and images that captured not only scientific facts, but also human emotion. Laughter, a mother's kiss, a child saying hello. These were included to show that Earth is not just a planet of technology, but a home filled with relationships and feeling. The record reflects the idea that life expresses itself through connection, music, and shared experience. Voyager does not broadcast the Golden Record, it simply carries it. The record is attached to the spacecraft's body, detected by a metal cover designed to survive millions of years in space. If the spacecraft remains intact, the record may outlast Earth itself. Long after our planet changes or disappears, the Golden Record could continue drifting through the galaxy. The record's purpose is not to ensure contact. The chance that another civilization finds Voyager is extremely small. Instead, the Golden Record represents a philosophy that exploration is not only about collecting data, but also about offering something of ourselves. Sending the record was an expression of hope that curiosity is universal, and that communication is possible even across the emptiest regions of the galaxy. To imagine the Golden Record's role, picture a small bottle carrying a message, cast into an endless sea. The ocean is vast, and the bottle may never reach another shore. Yet the act of sending it reflects a belief in the value of sharing, of reaching outward, of leaving a trace of who we are. Voyager carries that bottle into the darkness. The Golden Record also places humanity within a larger context. It shows that Earth is just one world among billions, yet its inhabitants chose to introduce themselves to the universe. Even if the message is never heard, the record stands as a symbol of human curiosity, creativity, and the desire to be understood. As Voyager moves through interstellar space, the Golden Record remains its quiet companion. Together they form a connection between Earth and the wider galaxy, a reminder that even a small spacecraft can carry the voice of an entire planet. Voyage's increasing distance from Earth reveals something subtle about our planet. How small our influence becomes as we move away from the Sunday. The farther the spacecraft travels, the more the solar system shrinks into a single point of light, and the more Earth becomes just one faint part of a much larger structure. This shrinking perspective helps scientists understand our true place in the universe. From Earth, the solar system feels enormous. We measure space missions in millions of kilometers and treat the orbits of the planets as vast regions. But Voyager's journey shows that the solar system occupies only a tiny pocket within the Milky Way. As the spacecraft moved beyond Neptune and the heliopause, Earth's gravitational and magnetic influence faded rapidly. Even the sun's strong presence weakened until it became merely one star among billions. Voyager's instruments recorded how the environment changed with distance, how the solar wind thinned, how magnetic fields shifted, and how particles from the galaxy replaced those from the Sunday. These measurements reveal the boundary between our familiar environment and the wider galactic medium. Earth exists within a protective bubble shaped by the sun, but beyond that bubble lies a far older and more complex system of forces. Understanding this context helps us see Earth more clearly. On the cosmic scale, our planet is not the center of anything. It is one world in a vast system, orbiting an average star located on one spiral arm of a galaxy that stretches 100,000 light-years across. Voyager's distance makes this reality visible in a way nothing from Earth could. As the spacecraft continues outward, the signals it sends back reflect a universe that becomes less shaped by the sun and more shaped by the galaxy as a whole. This shift in influence also highlights how delicate Earth's environment is. The planet thrives because of conditions that exist only within a small region close to the sun. Beyond that region, temperatures drop, radiation increases, and the stability that supports life disappears. Voyager shows how quickly these conditions change. A few astronomical units beyond the planets, the familiar patterns of solar weather give way to quieter, colder, and more uniform space. To imagine this change, picture walking away from a village at night. The warm lights, the sounds, the activity all fade behind you. As the distance grows, the village becomes a small glow, then a faint sparkle, and finally, a point swallowed by the larger darkness of the landscape. Earth's influence fades in the same way. Voyager's journey lets us watch that fading in real time. By measuring the shape of the heliosphere and the conditions beyond it, Voyager helps rewrite our understanding of where fits within the galaxy. The spacecraft turns abstract numbers into lived experience. The loss of solar pressure, the rise of cosmic particles, the shift in magnetic direction. Each change marks a new layer of distance and perspective. Voyager's data reminds us that Earth is extraordinary, not because of its cosmic size or position, but because life emerged on such a small and fragile world. From Voyager's viewpoint, Earth is a distant, invisible dot, but the science it sends back helps us appreciate the uniqueness of that dot and the environment that supports it. As Voyager moves deeper into interstellar space, it carries the story of Earth's place in the universe, a story of humility, scale, and quiet perspective, revealed not by what we see, but by how far a single spacecraft can travel beyond our light. Voyager is often described as humanity's most distant ambassador, a small messenger carrying our presence into a region no human, animal, or machine has ever reached before. Its mission is scientific, but its distance gives it a symbolic role as well. It represents Earth far beyond the reach of our planets, traveling quietly through the galaxy on behalf of the species that built it. The idea of an ambassador usually suggests contact or communication. But Voyager's role is different. It does not negotiate, speak, or broadcast messages to distant civilizations. Instead, its presence alone is the message. It shows that a society on a small planet once built machines capable of leaving their birthplace. Voyager becomes proof of curiosity, evidence that humans looked outward and decided to explore. Voyager's long journey shapes this symbolic identity. The spacecraft has traveled for nearly 5 decades, surviving radiation, extreme cold, and the gradual loss of power. Its persistence mirrors human determination. Even as its systems grow older and weaker, it continues to send data home. Each transmission is a reminder that exploration continues, even when the explorer is small and fragile. The golden record strengthens Voyager's ambassadorial character. Attached to its body, protected by a metal cover, the record carries the sounds and images of Earth. Greetings in many languages, music from different cultures, and pictures of life on our planet form a quiet introduction. If another civilization ever finds Voyager, the record will serve as a gentle handshake across the dark, a message that Earth once existed, full of life and diversity. Yet the true significance of Voyager as an ambassador does not depend on being found. The galaxy is too vast, and the likelihood of an encounter is extremely small. Instead, its importance lies in the act of sending it. Voyager represents our willingness to step beyond the comfortable boundaries of our world. It embodies the belief that reaching outward matters, even without knowing what lies ahead. Voyage's distance also gives perspective on humanity. From billions of kilometers away, Earth is invisible. Its borders, conflicts, and divisions disappear. Instead, the spacecraft carries a unified picture of the planet, free from the filters of culture or politics. In this sense, Voyager represents not a specific nation or group, but all of humanity. To visualize this idea, imagine a lantern set afloat on a vast, dark lake. The lantern drifts farther and farther from the shore, until only a faint glow remains a reminder that someone lit it. Someone cared enough to send light into the night. Voyager is that lantern. Its quiet signal, traveling across the emptiness, reflects both our scientific capabilities and our emotional need to explore. As Voyager moves deeper into the galaxy, it maintains a connection to Earth through the faint radio waves that return to the deep space network. These whispers are small but meaningful. They show that even at the edge of the sun's influence, a machine built by human hands can still reach back and be heard. Voyager's role as an ambassador is therefore both practical and symbolic. It gathers scientific data about a region we could never study otherwise. At the same time, it stands as a gesture of curiosity, hope, and continuity. Long after its power fades and its instruments fall silent, the spacecraft will continue drifting through interstellar space, carrying with it the story of where it came from and the beings who sent it. Voyager's scientific instruments have spent decades collecting data that shaped our understanding of the solar system and the space beyond it. Even though the spacecraft is small and its tools are simple by modern standards, the information it gathered remains some of the most valuable in the history of space exploration. Each measurement carries insights that continue to influence science on Earth today. During its early journey, Voyager studied the giant planets Jupiter, Saturn, Uranus, and Neptune in unprecedented detail. Its cameras captured swirling storms, lightning-filled clouds, and the intricate structures of planetary rings. These images transformed our understanding of planetary atmospheres, revealing dynamic weather patterns and complex interactions between magnetic fields and flowing gases. Voyager also discovered active volcanoes on Jupiter's moon Io, the thick haze covering Saturn's moon Titan, and the icy surfaces of moons that may hold underground oceans. These findings changed how scientists think about the potential for life in the outer solar system. Before Voyager, many believed these moons were cold and inactive. The the spacecraft revealed them as worlds shaped by heat, chemistry, and geological forces. Beyond the planets, Voyager measured the solar wind, the stream of charged particles flowing outward from the sunday. It recorded how the wind flowed, shifted, and eventually faded as the spacecraft approached the edge of the heliosphere. These observations helped scientists understand how the sun interacts with the interstellar medium and how cosmic rays are blocked or redirected by solar activity. On Earth, this information supports many areas of science. Solar wind measurements help improve models of space weather, which protect satellites, power grids, and communication systems. Data from Jupiter and Saturn informs studies of giant planets around other stars, showing what kinds of atmospheres and magnetic fields might exist in distant systems. The discovery of complex moons sparked new missions to explore them, such as the upcoming Europa Clipper. Even Voyager's measurements in interstellar space have practical scientific value. By detecting changes in particle density, magnetic fields, and cosmic rays, the spacecraft offers the first direct data about a region humans have never reached. These readings help refine theories about the structure of the galaxy, the movement of energy through space, and the way stars influence their surroundings. To understand the impact of Voyager's data, imagine shining a flashlight into a vast, dark cavern. The beam does not illuminate everything, but it reveals shapes and textures that hint at the size and complexity of the space. Voyager's instruments provide that kind of illumination, narrow but deep, revealing patterns invisible from Earth. Although many of its instruments are now turned off to conserve power, the ones that remain active continue sending valuable information. Each bit of data carries the weight of decades of travel and represents a perspective no other spacecraft can match. Even simple measurements become meaningful when collected from the edge of the sun's influence. Voyager's scientific contributions show how exploration can reshape knowledge. A craft built with 1,970 seconds technology continues to guide modern research, supporting theories in astronomy, planetary science, and space physics. The data it gathered helps connect Earth-based science to the larger processes of the solar system and the galaxy. As Voyager drifts through interstellar space, it carries instruments that still whisper about the universe around it. These signals enrich our understanding of the cosmos and remind us that even the most distant explorer can expand the boundaries of human knowledge. Voyager's long life in space is not only a triumph of engineering, but also a testament to the people who have cared for it across nearly 5 decades. Behind the spacecraft's quiet journey is a team of scientists and engineers who have guided, repaired, adjusted, and protected it through countless challenges. Their persistence is a central part of why Voyager still operates today. When Voyager launched in 1977, many expected the mission to last less than a decade. The spacecraft was designed to visit Jupiter and Saturn, then send back data until its power faded. But as it performed flawlessly and continued traveling outward, mission planners extended its goals. Each new phase required the team to rethink how to use limited resources, manage dwindling power, and keep ancient electronics alive. The people operating Voyager face unique challenges. The spacecraft is too far away for real-time commands, so every instruction must be carefully planned and tested. Engineers simulate the spacecraft's aging systems on Earth, predicting how they will respond before sending commands that take nearly a day to arrive. This slow rhythm forces precision. Mistakes cannot be fixed quickly, and every action must consider the long communication delay. Power is one of the greatest constraints. As Voyager's nuclear generator weakens, the team must choose which instruments to keep running. Turning off a device is often irreversible. Engineers debate each choice, balancing scientific value with the need to keep essential systems alive. Heating is also a concern. Without enough power, the spacecraft's electronics could freeze. The team constantly adjusts power usage to maintain a delicate balance between warmth and functionality. Voyager's thrusters present another challenge. These tiny engines help keep the spacecraft pointed at Earth. Over time, they have weakened, and fuel is limited. Engineers found creative solutions, including reactivating older backup thrusters that had not been used for decades. Their success in doing so extended the mission by years. The people behind Voyager form a kind of generational relay. Many of the original engineers have retired, and new team members learn to operate technology older than themselves. Manuals, diagrams, and handwritten notes from the 1,970 seconds continue to guide modern decisions. The continuity of knowledge and dedication shows how exploration spans human lifetimes. To imagine the team's work, picture tending a fragile lantern drifting into the distance. As the lantern moves farther away, its light grows fainter, and the tools needed to maintain it become more limited. Yet the caregivers continue adjusting the flame, preserving it for as long as possible. Voyager's mission is sustained by that same quiet persistence. The effort behind Voyager also reflects a particular philosophy of engineering: respect for longevity, careful planning, and the belief that even small steps forward can lead to extraordinary achievements. The spacecraft survives not only because it was built with care, but because teams of people chose to keep listening and keep working. Voyager's long mission shows that exploration is not a single event, but an ongoing relationship between humans and their machines. Every signal the spacecraft sends home carries both scientific information and the legacy of everyone who has supported it. The mission's endurance demonstrates how collaboration, patience, and creativity can extend the life of a tiny craft far beyond its intended limits. As Voyager continues drifting into interstellar space, the people guiding it maintain the connection. Their work ensures that the spacecraft remains a part of human history, a reminder that even the most distant explorer depends on the commitment and care of those who remain on Earth. Voyager's future can be understood only on the scale of deep time intervals, far longer than human history. Although its power will fade and its instruments will eventually fall silent, the spacecraft itself will continue moving through the galaxy for thousands, millions, and even billions of years. Its motion is simple and steady, guided only by the momentum it gained during its launch and the gentle pull of the sun's gravity. In the next 1,000 years, Voyager will drift far beyond the outermost traces of the solar system's influence. By then, the sun's magnetic field will no longer shape its surroundings in any measurable way. The spacecraft will travel through a region where the galaxy's magnetic patterns dominate, encountering particles and fields shaped by distant stars rather than by the sunday. This distance will place Voyager deeper into true interstellar space, where its path becomes part of the Milky Way's broader currents. Over the next 10,000 years, Voyager will move tens of trillions of kilometers farther. Its distance from Earth will grow so large that even light will take weeks to reach it. By this point, the spacecraft will pass near the outer edge of the local interstellar cloud, a region of slightly denser gas that surrounds the solar system. Voyager's silent presence will mark the slow outward drift of a machine that once carried voices and images from Earth. The long-term trajectory shows that in about 40,000 years, Voyager will pass relatively close to a star called Gliese 445. Even this encounter is not truly close. The spacecraft will still be more than a light year away. But on a galactic scale, this is considered a near pass. Gliese 445 is moving toward our solar system, while Voyager is moving outward, and their paths will bring them into the same region of the galaxy for a brief moment. Voyager will not stop or change direction. It will simply pass by in silence. If the spacecraft continues undisturbed, it will complete a slow orbit around the Milky Way in about 225 million years, carried along by the galaxy's rotation. During this vast period, stars will be born and die, constellations will shift, and Earth's continents will change shape. Yet Voyager will remain a small, cold traveler, following the gravitational currents like a grain of dust drifting in a vast celestial river. To imagine these timescales, picture a leaf caught in a slow, endless stream. The leaf moves gently, shaped by currents too large to see. It drifts past stones, bends, and quiet pools, continuing onward even when the landscape changes completely. Voyager's future follows this same quiet pattern, simple motion guided by gravity, unaffected by time's passing. Although Voyager's instruments will not survive to record these distant eras, the spacecraft itself may remain intact for hundreds of millions of years. Space between the stars is mostly empty, giving Voyager a chance to travel untouched for longer than any human monument or artifact could last. Long after life on Earth has evolved, changed, or disappeared, the spacecraft will still wander through the galaxy. Thinking about Voyager's distant future places human existence into perspective. The spacecraft is a reminder that even a small object, once set into motion, can continue traveling on scales far beyond the span of civilizations. Its endurance shows how exploration connects brief human moments with the enormous timeline of the universe. Voyager's future is not defined by destinations or arrivals. Instead, it is a quiet continuation, a journey shaped by simple physics and immense time. As it drifts through the galaxy, it becomes part of the Milky Way's long, slow motion, carrying a silent trace of its origins for millions of years to come. Voyager's long journey will eventually bring it near another star, an encounter measured not in thousands, but in tens of thousands of years. According to its current trajectory, the spacecraft will pass closest to a small star called Gliese, 445 inches, about 40,000 years. This encounter will not be a meeting in the familiar sense. Voyager will not approach close enough to see planets or interact with the star's environment. But on the scale of the galaxy, this will be one of the nearest points in its distant future. Gliese 445 is located in the constellation Camelopardalis. It is a red dwarf, smaller and cooler than the Sunday. Red dwarfs are the most common stars in the Milky Way. long-lived and quietly burning their fuel over trillions of years. Gliese 445 itself is moving toward our solar system, while Voyager is moving away from it, and this motion causes their paths to slowly converge. When Voyager passes near Gliese 445, the distance will still be vast, more than a light year. At this range, the star will not appear significantly brighter than the others around it. The spacecraft will simply drift through a region of space that happens to lie closer to this star than to any other. There will be no gravitation capture, no orbit, and no interaction. Voyager will continue on its path unaffected, guided only by the momentum it has carried since its launch. Although the encounter is distant and silent, it holds scientific meaning. Mapping this future passage helps astronomers understand how objects travel through the galaxy. Stars move through space just as planets orbit the sun, and over thousands of years, their motions change the relative distances between them. Voyager's path becomes part of this dynamic map, showing how interstellar travelers drift with the motions of stars. To imagine this passage, picture two small boats floating on a wide, slow-moving ocean. They do not aim for one another, but the large currents of the water gradually bring them into the same region before carrying them apart again. Voyager's encounter with Gliese 445 follows the same gentle pattern, guided not by intention, but by the long, steady motion of the galaxy. The vast separation during the encounter also shows how empty interstellar space truly is. Even when two objects pass relatively close by cosmic standards, the distance remains far greater than anything familiar to human experience. Voyager will not see planets or debris, and it will not enter a new solar system. Instead, it will simply drift through a region slightly influenced by the star's gravity. This distant encounter underscores the scale of Voyager's journey. 40,000 years is longer than all recorded human history. Civilizations will rise and fall on Earth long before the spacecraft reaches the vicinity of Gliese 445. The star itself will continue burning quietly, while Voyager, silent and unpowered, glides past it. After passing Gliese 445, the spacecraft will continue moving into new regions of the galaxy. It will slowly shift into different neighborhoods of stars, carried along by the Milky Way's rotation. Nothing will interrupt its motion unless it encounters a rare collision with dust or debris, an unlikely event in the vast emptiness of space. The predicted approach to Gliese 445 helps place Voyager's journey into context. Its path is not a route toward a destination, but a slow movement through the galaxy's immense structure. Each future encounter, even distant ones, reminds us how the motions of stars shape the landscape of the Milky Way. Voyager's future near Gliese 445 is quiet, uneventful, and meaningful in its own subtle way. It reflects the spacecraft's role as a long-term traveler, a silent witness to the slow dance of stars across deep time. The question of whether another civilization could ever find Voyager reaches into both science and imagination. The galaxy is immense, filled with hundreds of billions of stars, each with its own planets, debris, and drifting particles. Against this backdrop, Voyager is extraordinarily small, a metal craft no larger than a modest Earth vehicle, moving silently through interstellar space with no lights, no engine, and no beacon. Yet the possibility, however small, invites reflection on how discovery works on cosmic scales. The probability of an encounter is extremely low. Interstellar space is vast and mostly empty, with distances so great that even passing within a light year of another star is considered close. Voyager will drift for millions of years without approaching any planet or star closely enough to be noticed. Its path is not aimed at inhabited regions or targeted systems. Instead, it follows a simple outward trajectory defined by the gravity assists it received decades ago. For another civilization to find Voyager, several unlikely conditions would need to align. First, the spacecraft would have to pass through a region where an advanced species exists. Second, that species would need to explore space deeply enough to detect small objects traveling through interstellar space. Third, their instruments would need to be sensitive enough to notice something as faint and inactive as Voyager. Unlike a comet or asteroid, Voyager does not reflect much light, has no heat signature, and emits no active signals. Even with advanced technology, detecting such a small object would be difficult. It would require a civilization capable of mapping their local space with extraordinary precision, identifying tiny metallic objects among natural debris. If they succeeded, they might recognize that Voyager is not a natural formation. Its shape, materials, and construction would reveal that it was built by intelligent beings. If Voyager were discovered, the golden record attached to its body would become the key to understanding its purpose. The etched symbols explaining how to play the record, the pulsar map showing the location of the solar system, and the greetings in multiple languages would all signal that the spacecraft came from a technological society. The record's sounds and images, children laughing, wind blowing, waves crashing, would offer a glimpse into life on a distant world. But the record also presents a challenge. It requires the ability to interpret analog signals, understand mathematical patterns, and decode encoded images. A civilization different from ours might struggle to interpret the record's meaning, just as humans might struggle to understand an alien artifact. Yet the attempt itself could reveal shared curiosity. To imagine Voyager being found, picture a bottle drifting in a vast ocean. The bottle is small and the ocean is wide. The chance of it reaching another shore is tiny, but not zero. If someone ever discovers it, the bottle becomes a link between two distant places, evidence that somewhere across the sea, another society once existed. Voyager's future encounters, if they happen at all, will occur on timescales far beyond human civilization. Tens of thousands of years may pass before it enters a region where an advanced species might be present. By then, Earth will have changed, cultures will have evolved or vanished, and the world may look nothing like it does today. The value of considering this possibility is not in predicting contact, but in recognizing the meaning of sending Voyager in the first place. The spacecraft carries a message meant for any potential neighbor in the galaxy. The act reflects a belief that communication, even across impossible distances, has worth. Whether or not anyone ever finds Voyager, the spacecraft continues to move outward with the quiet dignity of a messenger. Its journey reminds us that exploration is an open gesture, one that does not require a response to hold meaning. Voyager travels faster than any human-made object before it, yet its speed becomes almost small when measured against the scale of the universe. This contrast reveals how different human motion is from cosmic motion, and how even our fastest machines move gently compared to the natural forces shaping the Milky Way. Voyager moves at more than 15 kilometers per second. On Earth, this speed would carry an aircraft around the planet in a few hours. It is fast enough to escape the sun's gravitational pull and reach the outer solar system in just a few decades. But when that speed is placed alongside the speed of light, 300,000 kilometers per second, it becomes clear that Voyager is moving at only a tiny fraction of what the universe considers fast. Light from the sun reaches Earth in 8 minutes. Light traveling from Earth to Voyager now takes more than 18 hours. This delay shows not only the spacecraft's distance, but also the difference between human-made speed and the natural speed of energy in the universe. Cosmic events such as supernova explosions, stellar winds, and high-energy particles move at near light speeds, crossing distances that would take Voyager tens of thousands of years. Compared to the motion of stars, Voyager is also slow. The sun itself orbits the center of the Milky Way at more than 200 kilometers per second. Every star in the galaxy follows its own path, creating a vast rotation pattern that takes about 225 million years to complete. Voyager is carried along in this motion, like a small leaf drifting in a much larger current. Even though it travels outward, it is still part of the galaxy's long, graceful orbit. Voyager's speed is also different from the speeds of natural cosmic travelers. Comets falling toward the sun and reach hundreds of kilometers per second. Jets of gas from black holes can approach the speed of light, and gravitational waves ripple across the universe at light speed, carrying information about events billions of years old. Against these forces, Voyager moves steadily but quietly fast by human standards, gentle by cosmic ones. To picture this contrast, imagine standing beside a river. A small boat is drifting downstream at a calm pace, while the deeper current beneath it moves far faster. The river itself winds across mountains and valleys, shaping the landscape over long periods of time. Voyager is like that boat, moving on its own, yet also carried by the galaxy's much larger motion. This comparison does not diminish Voyager's achievement. The spacecraft proves that human engineering can send a machine across the solar system and into interstellar space. But understanding speed on a cosmic scale reminds us how immense the universe truly is. Even a craft traveling at 15 kilometers per second needs tens of thousands of years to approach the nearest stars. Voyager's slow progress across the galaxy is part of what gives its journey meaning. Speed is not the goal. Instead, the mission shows how steady motion, guided by simple physics, can carry an object across unimaginable distances. In a universe where light travels instantly and stars move swiftly, Voyager drifts with a quiet persistence that reflects the human spirit of exploration. By comparing Voyager's motion to the speeds of light, stars, and galactic rotation, we understand both the limitations of our technology and the grandeur of the cosmos. The spacecraft's slow, constant movement becomes a reminder of the scale of space and the patience required to explore it. Voyager's journey offers more than measurements and scientific discoveries. It offers a way to think about time, distance, and what it means to be human. As the spacecraft drifts through interstellar space, Its quiet motion reflects ideas far larger than its small metal frame. It becomes a symbol of curiosity, persistence, and the human desire to understand the universe beyond our immediate surroundings. Time behaves differently on Voyager's scale. The spacecraft has been traveling for nearly 5 decades, yet this is only the first moment of its long future. Long after its instruments fail and its power fades, Voyager will continue moving through the galaxy for millions of years. Human history is short compared to this timeline. Civilizations rise and fall within a few thousand years. But Voyager's path stretches far beyond them, carrying a trace of our existence into an unknowable future. Distance takes on new meaning as well. Even after covering billions of kilometers, Voyager has barely begun to cross the space between stars. The spacecraft reminds us that the universe is vast in a way that challenges human intuition. On Earth, distances are measured in steps or kilometers. In the cosmos, distances are measured in light-years units, so large that even light itself requires years to travel them. Voyager's slow progress across this space highlights the scale of the galaxy and the patience required to explore it. Voyager also teaches us something quiet about perspective. From Earth, we see ourselves as the center of our story. Our cities, landscapes, and daily routines feel large and important. But from Voyager's viewpoint, Earth is invisible. The spacecraft carries no sense of borders, nations, or conflicts. It carries only the memory of where it came from and the golden record attached to its side, a message that reflects not our divisions, but our shared humanity. To imagine Voyager's place in the universe, picture a small spark drifting away from a campfire at night. The spark rises, carried by a faint breeze, moving farther until it disappears into the dark sky. The campfire continues, and life around it goes on, but the spark travels independently, taking with it a moment from the fire's warmth. Voyager is that spark, a tiny piece of Earth drifting into the galaxy, carrying the story of its origin, even as it moves into places untouched by human presence. Voyager's journey also offers a reflection on fragility and endurance. The spacecraft was built by human hands, using technology from the 1970 seconds. Yet it has lasted far longer than expected. Its endurance mirrors the resilience of human curiosity, the drive to explore, to learn, and to send something of ourselves into the unknown. Even as its systems weaken, Voyager continues to send faint signals home, each one a quiet reminder of what we can achieve. In a philosophical sense, Voyager represents a question we often ask about ourselves. How far can a single action, a single creation, a single gesture reach? The spacecraft moves through the galaxy long after the people who built it are gone. Its path shows how human effort can extend beyond individual lifetimes, connecting one moment of exploration to the deep timeline of the universe. Voyager teaches us that being human is not defined by our size or the limits of our world, but by our willingness to reach beyond them. Its journey blends science with meaning, showing that exploration is both a physical act and a reflection of our nature. As Voyager drifts farther into the darkness, it carries a message written not only on the golden record, but in its existence itself. curiosity endures, and even the smallest traveler can reveal the vastness of the cosmos.